Good day. In this presentation, I will discuss the topic in the structure of polycrystalline aggregates, namely the size and strain separation. So to give the objectives of this presentation, I will discuss how the strain and size broadening effects on the diffraction peaks can be separated. So I will also describe how these factors can be separated using the Williamson-Hall method. So as we know, there are several factors that cause broadening in the diffraction peaks. These are crystallite size, presence of microstrain, and due to the instrument. So these factors are conveniently measured using the full width at half maximum of the diffraction peaks. So the full width at half maximum is in regions unit and calculated using the Scherer's formula. So from these factors, we can say that the experimental or the observed FWHM is equal to the sum of all these factors. So that is the equation represented here. So we can separately determine the instrumental broadening contribution by performing the same measurement on a fully annealed sample that is strain-free. So however, the problem of the diffractometers before is how the size and strain contribution can be separated when both effects are present. So with this, the Williamson-Hall method is used. So the Williamson-Hall method involves the use of experimental full width at half maximum, or the BXP or the BOBS. So it provides the separate effects of size and strain. It is performed by plotting the BXP cosine theta versus the sine theta. So this is the equation for the Williamson-Hall method. So to clearly explain the Williamson-Hall method, let's consider an example problem. So magnesium oxide powder was ground by the wall milling process to produce a fine powder sample. With respect to this fine powdered sample, X-ray diffraction experiment using copper K alpha radiation with a crystal monochromator were carried out, and we found a decrease in peak height as well as the peak broadening. The values of full width at half maximum for the corresponding planes are summarized in the figure table on the right side. So first, let's express the full width at half maximum in terms of radians. So the values are represented in the table 1. So the cosine theta and sine theta were also calculated, and the product of the BXP and the cosine theta were also calculated, since this will be plotted in the y-axis for the Williamson-Hall method. So using the Williamson-Hall method, plot of BXP cosine theta as a function of sine theta was obtained. The following is represented in this figure. The equation and the linearity constant r squared is illustrated. So in the interpretation of the Williamson-Hall plot, the following are considered. So if the peak broadening is mainly due to the crystallite size, then the value of the PXP cosine theta will be constant and the curve will appear as a horizontal line. So on the other hand, if the peak broadening is mainly due to the presence of strain, BXP cosine theta is a linear function of sine theta, which is the case for our present problem. So note that the sample measured in this problem was ball milled magnesium oxide. So that is, it has significant number of strain present in the crystal lattice. Hence, the strain is the major contributor of the peak broadening for this current problem. So otherwise, when a fully annealed sample was measured, the plot will appear as a horizontal line as represented by the dashed red line in the figure here. So yeah, in the absence of strain. So thank you for listening.
In this video, we will talk about how to separate the size and strain components of peak broadening. The full width of half maximum, FWHM, of diffraction peaks are influenced by the crystallite size, microstrain, and instrumental effects. The relation depends on whether the peak is Lorentzian or Gaussian in shape. The terms are intuitively as follows. We have BEXP, or the experimentally or observed and measured FWHM, which would be equal to the combination of B sub size, FWHM due to crystallite size, B strain, FWHM due to microstrain, and B instrument, which is FWHM due to the instrument. B instrument can be determined by recording a diffraction pattern under identical conditions of the same substance that is in a well-annealed and large-grained condition. Separation of size and strain components can be done by using a Williamson-Hall plot, the details of which can be found in this paper. It utilizes b cosine theta as a function of sine theta. It implicitly assumes Lorentzian peaks. Linear regression is applied to the scatter plot, and the strain component is attributed to the slope, while the size component is attributed to the intercept. So in this figure, we have the Williamson-Hall plot for magnesium oxide and aluminum oxide. The two lines with a significant amount of slope are ball milled for 2 hours. Letter B corresponds to specimens that are ball milled for 2 hours, but are then annealed for another 2 hours. From this plot, we can say that magnesium oxide and aluminum oxide have similar crystallite size, since B sub size has something to do with the intercept. Ball milling produces less microstrain on aluminum oxide, as can be seen by the less pronounced slope, and annealing virtually relieves all of the strain, given by these horizontal lines for the B specimens. For this problem, we have X-ray diffraction results for magnesium oxide. 5 peaks with corresponding 2 theta and full width at half maximum in degrees are presented in Table A. We will apply the Williamson-Hall plot method to separate the broadening due to size and due to strain. So we have the given. First, we convert the FWHM from degrees to radians to obtain the observed broadening. Then we calculate the values of cosine theta and sine theta. The observed broadening is then multiplied to cosine theta. We plot sine theta on the x-axis and b cosine theta on the y-axis and apply linear regression. We find this equation and a corresponding r squared. Thus, the broadening due to strain is 0.0022, while the broadening due to crystallite size is 0.0021.
You heard how my students tackled the problem. Now, I am going to discuss more details of our example. The whole method equation is given by broadening b sub r times cosine theta is equal to 2 times eta times sine theta plus lambda divided by epsilon. The 2 times eta is the amount of inhomogeneous strain, while epsilon is the average value of the size of crystallites. Continuing with the problem, we read, similar X-ray diffraction measurements were made for magnesium oxide powder sample, which were fully annealed, so as to remove the lattice strain for comparison. The resultant full width at half maximum, or FWHM values of 5 peaks, are given in Table B. We note that FWHM is given in terms of degree. The correction for the instrumental width is calculated from the fully annealed sample. This is B sub I, or instrumental broadening, B instrument. Note that B sub I is given in terms of radians. The instrumental broadening factor is subtracted from the experimentally measured FWHM. Assuming Lorentzian peaks, we write the equation as experimental broadening minus instrumental broadening equals the broadening due to size and the broadening due to strain. And here is the Williamson-Hall plot, or the plot of B cosine theta as a function of sine theta. The blue dots correspond to the magnesium oxide that is ball milled without instrumental broadening. The green dots correspond to the magnesium oxide that is annealed. The solid lines represent the linear plots. Notice that the blue curve has a linear relationship between B cosine theta and sine theta, with an R squared of 0.97. This suggests that strain is the most important contribution for the ball milled sample. The size of the crystallite can be obtained using the y-intercept. The green curve is not a horizontal line, with an R squared of 0.57. We can say that not all of the strain is relieved. The crystallite size of the two samples is similar.